Alright, hi everybody. This is Module 5, Lesson 2. We're about to be hit by Hurricane Sandy and hope everyone rides out the storm okay. I'm going to try to present your lesson on video so that we don't get behind in class. And it's actually a really great week for a video lesson. It's always better to see you all in person. But the lab activity I had planned for today is not my favorite lab, so it's okay that we don't get to do it together. So let me tell you what you need to know about moles and stoichiometry and atomic mass units, and well, here we go. Okay, oh, and you were going to have a quiz today on elements 41 to 60. Make sure you keep studying for that. We'll have it next week. So, anyhow, today let's review what we did last week. Last week we talked about three major types of chemical equation. So you could have a formation reaction, and that is when you would take elements and form a compound. You could take sodium plus chlorine and form sodium chloride. Now, key things to remember when you have a formation reaction is to have homonuclear diatomics remain the way they are when they're elements. And then to balance your equation, we know according to the law of conservation of mass that every atom that's present at the beginning of a reaction must be present at the end of a reaction. We can see chlorine's not balanced. If we do this, chlorine is now balanced, sodium's not balanced. If we do this, then the equation is balanced at this point. Formation reaction, taking elements, forming a compound. And our coefficients here are the only things we can change when we balance an equation. We're not allowed to change the subscripts here at all. The next type of reaction that we studied last week, the decomposition reaction. You all saw last week the decomposition of water. You saw the decomposition of sugar, which was catalyzed by sulfuric acid, but the acid did not actually participate in the reaction. Decomposition reactions are taking a compound and breaking it down into its elements. We could just write the reverse reaction here, for example. The compound, sodium chloride ionic compound, decomposes into 2 sodium atoms and 1 chlorine molecule. The third and last type of reaction that we studied last week is the combustion reaction. Combustion reaction always has something that can react with oxygen in the air. So you have 2 reactants, the thing that is burning and the oxygen in the air. You also have always 2 products, the same 2 products, carbon dioxide and water. So we could choose something like methane gas. That's one of the simplest combustibles, CH4. You don't have to know that that's methane. But anything that you could burn wood, you could burn propane like we do in class, any type of combustible, and then always oxygen from the air is part of the combustion reaction. Remember that oxygen is a homonuclear diatomic. You always have the same 2 products, carbon dioxide and water, as long as it's a complete combustion. What that would mean, complete combustion, means that you have enough oxygen to fuel the reaction. If there's not enough oxygen, then you may have a situation where there's incomplete combustion, and we'll talk about that in just a moment. Then I always start balancing with non-oxygen and hydrogen things, carbon and carbon, 1 and 1, that's good. Then hydrogen, 4 hydrogens on the reactant side, only 2 on the product side, so I'll try to balance that this way. Then I have 2 oxygen on the reactant side and 1, 2, 3, 4 on the product side, so I need 2 there, and I think that gives us a balanced equation. So the combustion of methane, always add oxygen from the air, you always produce carbon dioxide and water. If you are required to write the phases for these reactions, of course, methane is a gas, which you wouldn't necessarily know unless you were told in the problem. You do know oxygen from the air is a gas, so you can always put that without being told. Also, during combustion reactions, the 2 products will always also be gases because the reaction is going to be exothermic or giving off a lot of heat. The products will be quite hot, so they'll be gases as well. So that's just a quick review of last week. Now, I mentioned I'd talk to you about incomplete combustion, which can be very dangerous and is also on the test. As a test question, you would want to know that with incomplete combustion, you would not have enough oxygen to fuel the reaction. When that happens, you will still have combustion occurring, but you will have not just these 2 products, but also several other products that can be poisonous. So the key to thinking about an incomplete combustion, whether it's maybe say having a gas burner that is running but not lit, maybe just a pilot light able to burn some of it. If you have a situation such as a not very well ventilated wood stove, even the propane torch we use in class, you can have a dangerous situation where you're producing not just carbon dioxide and water gases, but also carbon monoxide, which would be the most dangerous product of incomplete combustion. On the test question, you want to mention carbon monoxide by name, and you also want to make sure that you mention that incomplete combustion comes from not having enough oxygen present in the reaction to fuel the reaction properly. So just a review of last week. Make sure that you can identify or write these 3 types of reactions: formation, decomposition, and combustion. Also, I wanted to just review a little bit more because there are test questions about this. So, let's see. For example, we could ask you for a formation reaction, the formation of baking soda. So I would tell you baking soda is sodium hydrogen carbonate. So if I ask you, and it's a solid, of course, if I ask you to write the formation reaction for this particular substance, compound, then on the test you would need to do it. So pause right now, pause the video, try to write a formation reaction to form this as a product, and then turn it back on and see if you get it right. Make sure you balance your equation, make sure you consider homonuclear diatomics. Okay, so hopefully you're turning back on your camera now so you can see the solution. The formation of sodium hydrogen carbonate or baking soda would look like this. So you have sodium, a solid, plus hydrogen, which is a homonuclear diatomic and a gas, plus carbon, plus oxygen, which again is a homonuclear diatomic and a gas. That's a 3. Gives us sodium hydrogen carbonate baking soda. Now we have to check and see if we're balanced. 1 sodium on this side, 1 on that side. 2 hydrogens on this side, only 1 on that side, so we need to balance that. So I would first try putting a 2 there, then clearly a 2 there. So my hydrogen's balanced, my sodium's balanced. Carbon, only 1 on this side, 2 on this side, so we need to put a 2. And oxygen, I have 2 times 3, which is 6 on the product side, so I would need 6 on the reactant side. So that would give me the balanced equation for the formation of sodium hydrogen carbonate. Notice for formation reaction, I take the elements, 4 different elements in this case, just as they appear in nature as elements, and then I form one compound from them. Let's see, we could look at the decomposition of lead iodide. Lead iodide is this. Pb is lead, I2 is iodide. So pause the camera, try to write the decomposition of lead iodide, and then turn it back on and see if you're right. Okay, so you're starting your video again. Decomposition takes one compound and breaks it down into its elements. So for lead iodide, for example, we would take the compound lead iodide, break it down, lead, the metal, and iodine, which is a homonuclear diatomic. It's balanced the way it is, so that is easy and done. Next, let's look at the combustion of C6H6. This is hexane, very similar to the combustion of methane, but different to balance. And if we write a combustion reaction, what is our other reactant besides the thing that's burning? Well, it's always oxygen from the air. So we have to make sure to remember that. Then our products are always carbon dioxide and water, and then we need to check to see if our equation is balanced. So first I'll start with carbon, 6 carbons here, maybe I want 6 there. Then I have 6 hydrogens on this side, maybe I want, I don't want to end up with an odd number of oxygens, so I definitely want to perhaps multiply this by 6 instead of by 3, just so I don't end up with an odd oxygen. Okay, so 6 hydrogen, 12 hydrogen. So perhaps if I do this, alright, let's see. So now I have 12 carbon, 12 carbon, 12 hydrogen, 12 hydrogen. Now, 2 oxygen on this side. Let's see, I have 24 oxygen on this one and 6 on that. That's a total of 30 oxygen on the product side. So if I move my plus sign over a little bit, I want 15 oxygen on the reactant side, and that's the combustion of hexane. I think YouTube only allows 10-minute videos, so I'm going to stop here. I'll tell you the next problem is going to be getting the mass. Oh, we'll do that later. So I'm going to turn it off and come back with another 10-minute clip.